Hi, good morning everyone. In today's topic, we'll be talking about the Doppler effect. What is it, its uses, and how do we experience it in our everyday lives? So to start with, what is the Doppler effect? So the Doppler effect in simple terms is the change in frequency in relative to something or to a sound source that is moving. So the Doppler effect. It was named after an Austrian physicist, Christian Doppler, who described the phenomenon in 1842, a phenomenon affecting waves in frequency and wavelength. A change in frequency or wavelength of a wave in relation to an observer who is moving relative to the wave source. To properly visualize that kind of statement, I'll be showing you a demonstration or a video in the next slide.
Road. The horn to you might sound something like this. So it stops at a high pitch and moves to a lower pitch, even though from the driver's perspective the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up and so are delivered to you at a higher frequency, which you interpret as a higher pitch because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out and so you hear them at a lower frequency, a lower pitch. So that's how...
So, based from the video, so the Doppler effect is some kind of a phenomenon nga madungog nimo if let's just say nga some example, you are standing and na source of sound nga moving either away or padulong sa imuha, and now ka-notice kang if that source is making a sound, the closer or the farther it gets from you, magkalahi ang iyang tingog. The farther it is, the dimmer the sound is, and the closer it is, the higher the pitch of the sound is.
Part of our discussion, we're going to discuss all about the receding sound source. It's a pitch sound lower to an observer than the source actual pitch. When the sound source moves away from you, the sound waves are stretched, resulting in a longer wavelength and a lower frequency, resulting also to a lower pitch. Okay, Doppler effect formula. F is equal to the observer frequency, Fs is the source frequency, V is the speed of the sound in a medium, VO is the speed of the observer relative to the medium. Positive if the observer is moving towards the source, negative if moving away. Vs is the speed of the source relative to the medium, positive if the source is moving away from the observer, negative if moving towards. Okay, sample problems. So sample problem number 1, a car moving towards the stationary observer at a speed of 300 meters per second. The car horn emits a sound of frequency of 500 Hz. If the speed of the sound in air is 343 meters per second, what frequency does the observer hear? Where FO is unknown, Fs is 500 meters per second, V is equal to 343 ms, and Vs is negative 30 meters per second. It is negative because the source of the sound is moving toward the stationary observer. Okay, formula, observer stationary, frequency observer is equal to F times V times divided by V minus Vs. So the solution, 500 is times 500 times 343 divided by 343 minus 30, and F is equal to 500 times 343 divided by 313. Yes, is equal to 547.6 Hertz. So the observer hears about 548 Hertz. Okay, sample problem 2. A stationary observer hears a frequency of 510 Hz when the car approaches and a frequency of 450 Hz when the car moves away. If the speed of the sound is 340 meters per second, determine the true frequency of the car horn. When F approach frequency approach is equal to 510, frequency recede is 450. Formula, approaching or F approaching is equal to F times V divided by V minus Vs. Receding or the frequency receding is equal to frequency times V divided by V plus Vs. Shortcut of the formula of the true frequency solution, F is equal to square root of F approach times F recede. So square root of 510 times 450 is equal to square root of 229,500. The square root then squared. The answer is 479 Hertz. The car horn's actual frequency is 479 Hertz. Okay, the Doppler effect of light. Light travels at electromagnetic wave. Frequency determines the color. Higher the frequency is equal to blue, lower frequency is equal to red. Wavelength in the distance between wave crest. Higher wavelength corresponds to less energy, while shorter wavelength corresponds to more energy. Okay, blue shift approach. So, kung lower atong frequency, lower energy, high frequency, high energy. Mao po ni siya ang reason nga nung dugay kayo na na-achieve sa mga scientist ang kanang blue bulb kay lisod kayo ni siya lisod kayo ni siya kwaon kay high kayo ni siya frequency. So the Doppler effect, just like in a pitch of a car horn, changes in approaches or a move away, the observer wavelength of the light also changes. Decreased wavelength when the object moves towards the earth, and the light waves it emits get compressed, resulting to a shorter wavelength. Shift to a blue end. The blue end of the visible light spectrum consists of a shorter wavelength. High frequency and high energy, this shortening of the wavelength corresponds to increase in the light frequency and energy. When the light source moves towards you, the light waves are compressed, resulting in a shorter wavelength and a brighter frequency. Shift towards the blue end of the spectrum.
Redshift receding. This slide introduces the idea of redshift. Redshift happens when a light source is moving away from us. As the source moves away, the light waves get stretched out. The stretching makes the wavelength longer and the frequency lower. Since red light has longer wavelengths compared to blue light, we say the light is shifting towards the red end of the spectrum. This is why it's called redshift. A common example is when galaxies moves away from Earth. Their light appears redder than if they were at rest. Now let's proceed to the Doppler effect formula of light. Now to measure this effect, we use the Doppler effect formula for light. And the formula is the redshift is equal to the wavelength observed minus the wavelength rest over the wavelength rest. Here the z is the redshift. If z is positive, it's said to be the object is receding or moving away. If z is negative, the object is approaching. Now, the wavelength observed is the wavelength of the light we detect here on Earth, and the wavelength rest is the wavelength of the object emits if it were not moving relative to us. We also have here for slow speeds means much smaller than the speed of light. We can use a simple approximation, which is the redshift is approximately to the velocity over the speed of light. So this tells us that the redshift is basically the speed of the object divided by the speed of light. This makes it much easier to estimate the velocity from the redshift. So now let's proceed to our problems solving for sound and light. For the first problem, so let's practice with the sound example first, since it's easier to imagine. So the problem is a train is moving toward us at 25 meters per second, blowing its whistle at 400 hertz. We want to know what frequency we hear, and the speed of sound is given at 343 meters per second. Now we can use the Doppler formula of a moving source. Here Fs is the original frequency, and V is the speed of sound, and V is the source speed. And then since the train is moving toward us, then we subtract the source speeds to its denominator. Now let's plug in the numbers. So we got the F is equal to 400 times 343 divided by the 343 minus 25, and we have to continue. We get 400 times 343 over 318. And the final answer is about 431 hertz. So we hear a slightly higher pitch than a whistle original sound because the source is moving towards us and compressing the sound waves. So for our example number 2 is for the light. Now let's look at the same idea with light. The problem says a galaxy has a redshift of z is equal to 0.1. How fast is it moving away from us? So for low speeds we can use the approximation. The speed of the object is equal to the redshift times the source speed, and then we have to substitute the values. So redshift is equal to 0.1 times 300,000 kilometers per second, and this gives us the speed of the object as approximately 30,000 kilometers per second. So this galaxy is moving away from us at about 30,000 kilometers per second, which is about 10% of the speed of light. This shows how astronomers can calculate the motion of galaxies just by measuring their light.
Now let us move on to the applications of the Doppler effect in astronomy. So in astronomy, the Doppler effect is one of the most important tools. It allows us to measure how stars and galaxies move. It actually provided the key evidence for the expansion of the universe through something that we call the redshift. So the redshift, if you don't know what it is when a star moves or a galaxy moves far away from us, the light stretches and it turns or it shifts to red. And when a star or something or a galaxy is moving towards us, the light that it emits squeezes together and then it shifts to blue. Now, even small wobbles in a star's motion can reveal the presence of orbiting planets. So when astronomers discover exoplanets, they often use Doppler measurements. Next is applications in weather radar. So the Doppler effect is also used in weather radars. These systems send out microwaves which bounce back from raindrops. If the raindrops are moving, the frequency shifts, and that tells meteorologists the speed and direction of the storm. This technology even helps detect tornadoes before they even form. Now next, the applications on other uses. There are many everyday applications of the Doppler effect. Police use radar guns to measure car speeds, as mentioned by Ma'am Iris at meteorology, diba? Bats use it naturally in echolocation to hunt prey. Even speedometers and some navigation systems rely on Doppler shifts. So whether it's in hospitals or highways, in the sky or across the universe, the Doppler effect connects so many different parts of our lives, and that's why it's such a fascinating phenomenon. Now, to wrap it all up, the Doppler effect is simply the change in frequency we observe when there's motion between us and the source. With sound, that's why sirens or train whistles change pitch as they pass, and with light, it lets us measure how fast stars and galaxies move, and even showed us that the universe is expanding. What's amazing is that the same principle is used in weather, medicine, and even everyday tools like radar. It's a small idea with really big impacts. And that is all. Thank you for listening.